Class, in this toolbox we're going to talk about trigonometric functions. Trigonometric functions are really all about dealing with angles and waves. This is, of course, quite important in earth sciences. Whether we're talking about the direction of the wind, or periodic climate patterns such as the seasons or even El Nino, we wind up relying on trigonometric functions. Hopefully this is a review for most of you. But for those who have forgotten a lot of their trig, we're going to start off with a bit of a refresher. Alright, let's talk about those trigonometric functions, and really about angles generally. Let's start off with something simple. Imagine you're walking along a path, and your directions tell you to turn 45 degrees to the right, and then walk another mile. The question that you want to know is, where did you wind up at the end of your path? What coordinates? How far north and how far east did you go? Or in other words, how far did you go in the x direction and the y direction? To answer this question, let's think about how that 45-degree turn that you made relates to a right triangle, and how that right triangle in turn relates to your xy coordinates. I've added in two sides of this triangle. One is in red and one is in green. We refer to the red side of the triangle as the opposite side, because it is not touching the vertex that holds our angle theta. Note that this red side of the triangle is actually equal to the distance that we've traveled in the x or east direction. The green side of the triangle is referred to as the adjacent side of the triangle, since it touches the vertex that holds our angle theta. This green side of the triangle is also going to be equal to the distance that we've traveled in the y or north direction. And finally, we call the blue side of the triangle the hypotenuse. The hypotenuse is always the longest side of the triangle and is going to be equal to the distance that we've traveled. And real quickly, while we're talking about this angle, I'd like to make sure everyone remembers the relationship between radians and degrees. Pi is equal to the ratio of a circle's circumference to its diameter. 2 pi is also equal to the circumference divided by the radius. When we talk about angles in radians, we use pi. This is similar to talking about angles in degrees. There's a direct relationship between pi and degrees. 2 pi is equal to 360 degrees. This means that 90 degrees is equal to pi over 2, and 180 degrees is equal to pi. Trigonometric functions can be used to relate the lengths of the sides of a triangle to the angles of its vertices. So we can use these functions to determine how far we've gone in the x and y directions from the angle that we traveled. There are three basic trigonometric functions that you should already be familiar with. The sine function takes your angle as an input and gives you the ratio of the opposite side divided by the hypotenuse as an output. The cosine function takes your angle as an input and returns to you the ratio of the adjacent side to the hypotenuse. The tangent function takes your angle as an input and gives you the ratio of the opposite side to the adjacent side as an output. It's thus pretty easy to see how we could use these functions to figure out how far we've gone in the x and y directions. We know that we walked 1 mile, so our hypotenuse is 1. The length of the red side of the triangle, which is equal to our x-coordinate, can thus be determined by multiplying the sine of 45 degrees by our hypotenuse. Similarly, the length of the green side of the triangle, which is equal to our y-coordinate, can be determined by multiplying the cosine of 45 degrees by the hypotenuse. Please also note that 45 degrees is, of course, going to be equal to 1/4 pi. As you can see, it is thus pretty easy to figure out how far you've gone in the x and y directions if you understand these three basic trigonometric functions. These functions are really important, so let's examine them in more detail. First, I want to introduce the unit circle. The unit circle is nothing fancy. It's just a circle with a radius of 1. The only reason that we talk about the unit circle is that it makes our math easy, because it makes the hypotenuse always be equal to 1. So let's think about that angle in there. We can make that angle whatever we want, but we will always walk exactly 1 mile after making our turn. If we walk exactly 1 mile, then no matter what angle we turned, we'll wind up on the black circle. or on our unit circle. So we can think about changing that gold angle theta, and we can think about what that does to the length of the green and red sides only, since the length of the blue side will always be equal to 1. Now remember, of course, that sine is a function that takes in our angle and gives us the ratio of the red side to the blue side. The sine of 45 degrees is 0.71, so that tells us that the opposite side must be equal to 0.71 miles. The cosine of 45 degrees is also 0.71, so that tells us that the adjacent side is also equal to 0.71 miles. So in the example of a 45-degree turn, we've gone 0.71 miles north and 0.71 miles east. The next question you need to ask yourself is what those sine, cosine, and tangent functions actually look like. And we'll investigate this by changing that angle theta gradually and watching how that changes the length of the three sides of the triangles and hence the ratios of those triangles. We've now got our angle slowly increasing, and we can see the impact on the length of the sides of the triangles and hence on the three trigonometric functions. Let's focus first on the sine function. The sine function is equal to the length of the red side divided by the blue side. Of course, the length of the blue side doesn't change as we travel along the unit circle, so really it's just equal to the length of the red side. We can see that the red side starts off with a length of 0 when the angle is 0, but it grows rapidly. Once we've reached an angle of 90 degrees, or pi over 2, the red side has reached its peak length and starts to slowly shrink. Eventually at 180 degrees, or pi, the length of the red side reaches 0 again and then starts to go negative as we transition to the back side of the circle. We can easily see that once the angle reaches 360 degrees, or 2 pi, we'll start the pattern all over again. This is why the trigonometric functions are all cyclic. Next, let's take a look at the cosine function. The cosine function is the length of the green side divided by the length of the blue side. It starts off at 1 when your angle is 0, and it immediately starts to shrink until it reaches a value of 0 at 90 degrees, or pi over 2. And then it goes to negative 1 at 180 degrees, or pi, before it'll eventually start to get larger again. If you look at the function, it is really exactly the same as the sine function, except that it is shifted to the left by pi over 2 radians, or 90 degrees. This makes a lot of sense if you think about that circle. If we just rotated our circle 90 degrees, we would swap the green side of the triangle for the red side of the triangle. Next, let's look at the tangent function. The tangent function is equal to the opposite side divided by the adjacent side, or the red side divided by the green side. Since the sine is equal to the red side and the cosine is equal to the green side, this also means that the tangent function is equal to the sine divided by the cosine. So if you simply look at the functions above, you can get an idea of what it should look like. Anytime the sine function is 0, and anytime the opposite side length is 0, the tangent will be 0. On the other hand, if cosine goes to 0, the tangent function will go to either positive or negative infinity. Just so you can see this a bit better, let me blow up the tangent plot and run through this again. Remember, the tangent function is equal to the length of the opposite side in red divided by the length of the adjacent side in green. When theta is 0, the opposite side is 0, and the adjacent side is 1, so the tangent is 0 over 1, which is equal to 0. The opposite side starts to grow while the adjacent side starts to shrink as the angle gets larger, so the tangent starts to increase. Eventually, the green adjacent side approaches 0, so the tangent starts to rapidly increase and eventually reaches infinity as you divide by 0. Once you've crossed past 90 degrees, the adjacent side becomes a very small negative number that you're dividing the opposite side by, so the tangent function comes back in from a very, very negative number. As you move along, it continues to move towards 0 until finally you get to 180 degrees, where the opposite side is again equal to 0, and so is the tangent. From 180 degrees to 270 degrees, both the opposite and adjacent sides are negative, so the tangent is positive. As the tangent approaches 270 degrees, however, the adjacent side again approaches 0, so the tangent approaches infinity. After 270 degrees, it comes back in from negative infinity and passes to 0 at 360 degrees to repeat the pattern. Let's get away from the unit circle and look at an example where you might want to use these trig functions if you are out on a boat. You've probably never been out to sea before, but I've spent a lot of time on research vessels, and you know what? Things go wrong. Sometimes the line breaks and our expensive equipment sinks to the bottom of the ocean. Or maybe it's not a line that broke. One time we were out at sea and using an autonomous glider that was basically a robotic submarine doing automated patterns around our ship to measure properties in the plankton community around the water parcel we were studying. Well, anyway, this little glider suddenly disappeared, and when we looked at its log data, we found out that its final position and our ship's position matched up perfectly at the exact same time. We'd accidentally hit the glider with the ship, and after sending out one last distress call, the glider sank to the bottom of the ocean. Well, that glider was worth $100,000, and some of the oceanographic instruments that we use are actually worth a lot more. So sometimes it is worth trying to search the bottom of the ocean to find instruments that have sunk to the bottom of the sea, and then to try and retrieve and repair them. And it turns out that one of the most efficient ways to search for something on the bottom of the ocean is to use a spiral search pattern. The equation for a spiral can be pretty easily specified by making the radius a linear function of the angle. However, if we're going to plug this into a submarine and tell it where to go, we can't just give it a radius and an angle. We need to give it latitude and longitude, or xy coordinates. So let's remember that the sine of theta is equal to the opposite side of the triangle over the hypotenuse, and that the hypotenuse in this case is simply the radius. So we can write that the x-coordinate will actually be equal to the hypotenuse or the radius times the sine of theta. Similarly, the cosine of theta is equal to the adjacent angle times the hypotenuse or radius, so we can write that the y-coordinate will be equal to the radius times the cosine of theta. Remembering what we know about functions of functions, we can simply replace r of theta in the equations for x and y with a times theta. Now we can actually use these equations to plug in a search pattern. Note that the parameter a will basically determine how far out you go with each sweep around the circle. I'm going to go ahead and calculate this with a equals 1 divided by 2 pi. So if we assume that our radius is in units of kilometers, our search radius will increase by 1 kilometer for each circle. Let's go ahead and plot this now and watch how our trig functions change as we travel along this spiral. If we told a submarine to follow these xy search coordinates, the gold line in this animation is the search pattern that it would trace as it looks for our missing oceanographic equipment. But I want you to again focus on the lengths of the opposite, adjacent, and hypotenuse sides of the triangle that are made based on this search grid. Now let's look over to the left at the plots of the sine, cosine, and tangent functions plotted based on these diagrams. Remember that the sine is the opposite side over the hypotenuse, the cosine is the adjacent side over the hypotenuse, and the tangent is the opposite side over the adjacent side. This time, of course, the hypotenuse is not staying at 1. We're no longer on the unit circle. The hypotenuse is growing over time as we move out on the spiral. However, those plots on the left still look exactly the same. That's because the sine, cosine, and tangent functions are functions only of theta. The specific lengths of the sides of the angles are not important because they increase proportionally as the radius gets larger. Their ratios, therefore, are only a function of theta. If you're unclear on this, I recommend that you rewind and watch this slide again until you've really developed some intuition with how these functions work. Alright, now that we have a good feeling for the sine, cosine, and tangent functions, let's talk about their inverse functions. Hopefully nobody has forgotten the concept of an inverse function. Inverse functions take the output of some other function and give you back the original input. There are many reasons why we might want inverse functions for sine, cosine, or tangent. For instance, let's say we're directing an airplane full of meteorological sensors towards a hurricane. We know the coordinates of the hurricane and we want to tell the plane what angle it needs to turn towards to head at the hurricane. We'll want to take the XY coordinates, which define the adjacent and opposite sides of a triangle, and use them to get the angle back out. Since sine and cosine take an angle and give us the ratios of the sides of a triangle, if we already have the ratios of the sides of that triangle, then the inverse functions for sine or cosine should be able to give us the angle. However, there's one issue. Remember, we mentioned before that you can only get a true inverse function if there is one-to-one matching of input and output. If one output has many inputs, you don't have a true inverse function. Of course, it's very clear from looking at these functions that there is not a one-to-one matchup between the inputs and outputs. In fact, there are an unlimited number of inputs that can result in the same output because these functions are cyclic. Okay, so that means that the inverses of these trigonometric functions cannot be true functions. They can't give us only a single output for one input. So what should we do? Well, let's focus first on the sine function and think about its inverse. If we call our function f of x equals sine of x, then f of 0 is 0, but f of pi is also 0, and f of 2 pi is 0, and f of 3 pi is 0. You get the picture. No matter which of those inputs we stick into our function, we get the output of 0. So what should the inverse function give us? Remember, it doesn't know what we put in the purple box. It only knows what we got out of the purple box. So if we put in 0 and got out 0, the yellow box for the inverse function can only give us the f inverse of 0, and we want that to be 0. But if we put pi into the purple box and get 0 out, the yellow box has to give us the same f inverse of 0. It can't be 0 one time and pi the next time. But what if instead we ask them to give us all the possible outputs that match that input? What if instead of just giving us 0 or pi or 2 pi or 3 pi, it gave us 0 and pi and 2 pi and 3 pi and 4 pi and 5 pi and 6 pi? This is really the most appropriate thing for us to expect from these inverse trigonometric functions. We can never know which of those angles we put into f of x, but we can see all the possibilities come back out of f inverse of x. So let's talk about how this actually works in practice. There are well-defined functions for the inverse trigonometric functions that are available in most calculators. The inverse trigonometric function is usually written on calculators or computers as sine to the negative 1 of x, as shown here. If you plug this into your calculator, it'll probably give you these values. This is really pulling out the portion of the sine function from negative pi over 2 to pi over 2, and giving us the inverse of that portion of the function only. But of course, we're really interested in all the possible answers. So let's think about what the inverse sine function actually looks like. If we continue the function upwards, we see that we can now find the other values we can get for x equal to 0. We get 1 at 0, pi, 2 pi, etc. This is pretty easy for the value 0 because the way that the sine function works. But what if instead we ask for the values of, let's say, the inverse sine of negative 0.5? If we look at the values we can get, if we enter in a value of negative 0.5, they're equal to negative pi over 6, 7 pi over 6, 11 pi over 6, 19 pi over 6, etc. If you think about this pattern of repeating every 2 pi, and combine it with the fact that the sine function is actually symmetric about the points pi over 2, we can write a general equation that gives us all the possible solutions. A general answer for all of the possible values that could satisfy the inverse of the sine function would include inverse sine of x, and note that this is the inverse sine value that you would get out of a calculator, and then plus 2 times pi times n. N here represents any integer. So we really have an infinite set of solutions here that repeat every 2 pi. Our solutions also include the set of solutions formed by pi minus inverse sine of x plus 2 times pi n. We need both of these equations because, as you can see from looking at the sine graph, through every repetition of our wave, we get 2 points at which the output of sine of x equals -1/2. Let's take a moment now and go back to our unit circle, just to see what these angles that we're getting actually look like. As our angle spins around, remember that we're waiting for sine of the angle to equal -0.5, which will happen when the opposite side has a length of -0.5. This first occurs at an angle of 210 degrees. So once we get here, we've reached one solution for the inverse sine of -0.5. However, if we keep spinning, we rapidly get to another solution at theta equals 330 degrees. Sine of 330 degrees and sine of 210 degrees are both -0.5. They both have associated x-coordinates of -0.5. However, one has a positive y-coordinate and the other has a negative y-coordinate. If we continue around some more, hopefully you'll expect that you'll get another solution at 210 degrees plus 360 degrees, which equals 570 degrees, and then another one at 330 degrees plus 360 degrees, which equals 690 degrees. And you'll keep getting them as you go around and around. Keep in mind that if you tell our hurricane hunter to turn 210 degrees or 570 degrees, you're telling her exactly the same thing. However, telling her to turn 210 degrees or 330 degrees will send her in very different directions. One will take her towards the hurricane, and the other will waste her time. This is something to always keep in mind when solving the inverse trigonometric functions. It's always good to check your angle and see if everything makes sense, because there are multiple answers, and some of them are what you want, but some of them aren't, because of this periodicity of the trigonometric functions. The next topic that I want to cover is the period and amplitude of a wave. But first, let's take a moment to talk about the tides. We're all familiar with the tides coming in and going out. Tidal patterns are actually quite variable around the world because they get affected by the shape of the coastline. However, the most basic pattern is what's referred to as a semi-diurnal tide. Semi-diurnal cycles are cycles with roughly 2 approximately equal high and low tides every day. The tides are caused by the gravitational pull of the moon and, to a lesser extent, the sun. The gravitational pull of the moon exerts unequal forces on different parts of our planet. The portion of the Earth closest to the moon feels the strongest gravitational pull because it is closest. The portion of the Earth farthest from the moon feels the weakest gravitational pull. The result is that the oceans actually bulge outwards towards the moon and directly away from the moon. As the Earth spins, this bulge seems to move around the planet, causing the tides. You might think based on this that you'd get 2 high tides and 2 low tides every day, leading to a period of 12 hours. Of course, that's not exactly true, because while the Earth spins once per day, the moon is also revolving around the Earth, leading the period of the tides to be slightly longer at roughly 12.5 hours. Okay, so let's say you want to come up with a function to describe the tides so that you can make accurate predictions for things like going out to tide pools to collect some sea stars or anemones. So far, we've worked with trigonometric functions that have a period of 2 pi or 360 degrees, depending on whether you're talking in radians or degrees. But we want a tide with a period of 12.5 hours. How do we modify the period of a trigonometric function? Well, what if we think about a function within a function? Let's define a function f of theta equals sine of theta. The period of this function will be 2 pi. But now let's go ahead and write theta as a function of time. We know that our normal period is 2 pi, and we want our period to be 12.5 hours. So let's say that theta equals 2 pi divided by 12.5 times t. This means that theta will now move more slowly than t, and it will only increase by 2 pi after a period of 12.5 hours. Now we can create our new function, g of t equals f of theta of t, and plug theta of t into f of theta to evaluate the period of our tides as a function of time. If we plot this now, we find that we do in fact have a function with the appropriate period of 12.5 hours. However, there is still one issue. If we look at this plot, it has an amplitude of exactly 1. The amplitude is the distance between the top of the wave and the middle of the wave, or half the distance between the crest and the trough. Now this would be okay if the height difference between our high tide and our low tide was exactly 2 meters. However, it's probably not. Here on the Gulf Coast, our tides are normally weaker than that. Let's say that our amplitude is actually half a meter. How can we write a function that has a lower amplitude? Well, if you look at this graph, if all you wanted to do was make both your crest and your trough less extreme, or in other words, make them closer to 0, you can just multiply the entire function by a value that is less than 1. So let's try defining a new function. We'll make h of t equal to 0.5 times g of t, which then means that h of t equals 0.5 times sine of 2 pi divided by 12.5 times t. Now if we graph h of t, we see that it doesn't get as high as g of t. It has a smaller amplitude like we wanted, and we've now got a graph of semi-diurnal tides. But of course, if you're actually familiar with tide pooling, you'll note that we're still missing something here. In this graph, all of our high tides and low tides are exactly the same strength. This isn't exactly how the tides work. We have what's known as spring tides, which are very strong tides, and neap tides, which are very weak tides. Spring and neap tides are caused by the fact that tides respond not only to the moon's gravitational pull, but also to the sun's. If you look at the video on the top right, you'll see that as the moon is orbiting the Earth, it is sometimes on the same side as the sun, sometimes on the opposite side as the sun, and sometimes at right angles to the sun. When it's on the same side as the sun, or directly opposite the sun, the gravitational bulges caused by both are additive, and we have those strong spring tides. However, when the moon is at right angles to the sun, we have the weaker neap tides. The length in time between one spring and one neap tide is approximately 7 days, so the time separating two spring tides is 14 days. So in other words, the period is 14 days. Really quickly, I just want to rewrite h of t so that it is in units of days rather than hours, because this will make things less confusing going forward. Now I mentioned before that the gravitational pull of the moon and the Earth are additive. This means that the tide themselves are actually the effect of two waves adding together. We've already written the equation for one of those waves, specifically h of t is the wave caused by the moon's gravitational pull. Now let's write an equation for the sun's gravitational pull. We'll call it s of t, and it will be equal to a times the sine of 2 pi divided by 14 days times t. In this case, a is the amplitude, which I've not specified yet. However, the sun's gravitational impact on the tides is typically about half that of the moon's, so let's go ahead and replace a with 0.25. And then let's graph both of these functions. We've got the moon's gravitational impact in red as h of t and the sun's gravitational impact in green as s of t. So now we've got a wave with a period of about half a day that is fairly strong, and we've got a much weaker wave with a period of 2 weeks. Now we want to think about how those two functions go together. During neap tides, what's actually happening is that the amplitude of the waves gets smaller, and during spring tides the amplitude gets bigger. So it makes sense to put the sun's impact into the overall function in the place of the amplitude. So I'm going to call our overall function for the tides k of t. In the new equation, I've multiplied h of t by a value of 2 times 0.5 plus s of t. Remember that s of t went from negative 0.25 to 0.25. So 2 times 0.5 plus s of t will go from 0.5 to 1.5. So that will make the overall wave vary in amplitude from half its original strength to 50% greater than its original strength. This now gives us a nice functional form that we can graph to see the tides. We could also go ahead and plug in a time of 10 years into the future if we wanted to and predict what the tides will be at that time. And if I get rid of h of t and s of t from this graph for a moment, we can start to clearly see where the spring and neap tides fall on this figure. Okay, this lecture has introduced a lot of trigonometric concepts, but hopefully many of these were already familiar to you. And if they weren't, we will definitely be working with them more in class this week. For now, please don't forget to take the mini quiz on Canvas.